In the last video, we saw reactions that proceed through a holonium ion intermediate. And in those reactions, the two groups add to the alkene in two different steps. The alkene attacks the electrophile, and then the nucleophile attacks to open the holonium ion. In this video, we'll look at reactions where both groups add to the alkene at the same time in a concerted addition. And our first example of a concerted addition to an alkene is a hydroboration oxidation reaction. And in this reaction, we treat an alkene with borane, BH3, and then with hydrogen peroxide, H2O2, and a hydroxide, OH-, a strong base. And this forms an alcohol product. And here, unlike the reactions we saw in the last video, the alcohol forms on the less substituted carbon. It forms with the opposite of Markovnikov selectivity, or anti-Markovnikov regioselectivity. In these reactions, borane is the electrophile. Borane has only 6 electrons and an empty p orbital. So the nucleophilic alkene attacks the empty p orbital of boron. At the same time, one of the hydrogens on the boron attacks the alkene, or transfers to the alkene. And because these bonds break and form at the same time, we call this a concerted reaction step. And in this concerted reaction step, the boron will add to the less substituted carbon, and the hydrogen will add to the more substituted carbon. And this is due to sterics. It's due to the size of the BH2 group. It's big enough that it will prefer to avoid other large groups, and so it will prefer to add to the less substituted carbon of the alkene. And this gives rise to the anti-Markovnikov selectivity that we see in these reactions. In the last reaction step, the base and hydrogen peroxide replace the boron with an OH group to give the final alcohol product. Another concerted addition reaction that we'll see is the reaction of an alkene with MCPBA to form an epoxide. MCPBA is metachloroperoxybenzoic acid, and it functions as an oxygen atom donor, as we'll see in a minute. This is a concerted reaction, and both carbon-oxygen bonds of the epoxide must form on the same face of the ring. In the addition of MCPBA to an alkene to form an epoxide, all bond breaking and forming steps happen at the same time. The reaction is concerted. In the concerted reaction step, the alkene attacks the oxygen of the peroxide, of the MCPBA. And when it does, the oxygen-oxygen bond breaks, and the electrons move to form a new carbon-oxygen pi bond. The existing carbon-oxygen pi bond attacks the hydrogen or the proton. And then finally, the OH bond breaks, and the electrons in that bond form a new carbon-oxygen bond. This flow of electrons results in a 3-membered ring containing an oxygen. We call that an epoxide. And then the carboxylic acid is also formed as a byproduct. The nature of the concerted addition means that both bonds to the oxygen of the epoxide must be on the same face of the ring. The third concerted addition that we'll see is a hydrogenation reaction. And in particular, we'll look at hydrogenation reactions that occur on metal surfaces, reactions that use hydrogen gas, or H2, along with a metal catalyst. And the most common metal catalyst that you'll see for these reactions is palladium on carbon, written as palladium/carbon. These are heterogeneous catalysts, meaning they don't dissolve in the reaction mixture, and so the reaction happens on the metal surface. We'll imagine the metal surface to be this black square here, and the hydrogen comes in and adsorbs to the surface. Okay, then the alkene comes in and also interacts with the surface. And as the alkene is positioned there, it attacks the hydrogen. Another hydride attacks the alkene, and both of these steps happen at the same time and to the same face of the alkene. And this gives rise to an alkane, where both of the new carbon-hydrogen bonds are formed on the same face of the structure. The hydrogenation occurs with syn selectivity. Because this reaction happens at the surface, the sterics, the bulkiness of the surface, cause two things to happen. First, the hydrogen will add to the less bulky face of the alkene if the two faces are different. The less bulky face is more accessible and can more easily approach the surface of the catalyst. Second, less substituted alkenes will react faster than more substituted alkenes, again because they can more easily approach and interact with the catalyst surface. Let's try an example. Take a minute to draw the isomers, any regioisomers or stereoisomers that are formed in the reaction shown. Because this is a concerted addition of H2 to an alkene that occurs on a surface, the two hydrogens will add in a syn fashion. They will add to the same face of the alkene. When the hydrogens add to the alkene, they can add to the top or bottom face. So here we'll draw the product where the hydrogens add to the bottom face. Then we also need to draw the product where the hydrogens add to the top face. These two products are stereoisomers. They're enantiomers. These hydrogenation reactions will proceed to form a mixture of enantiomers. Now we've seen three different reactions in detail that all proceed through a concerted mechanism. There are others that will also proceed through this type of a pathway, and here we'll look at three more, but in less detail. And we'll start with the oxidation of an alkene with OSO4, or osmium tetroxide. This reaction will form a cis diol, meaning two alcohols are added to an alkene, and they're added with syn stereochemistry. They're added to the same face of the alkene. In these reactions, the nucleophilic alkene attacks an oxygen of the osmium tetroxide complex. At the same time, the electrons in that osmium-oxygen bond move to osmium, and the other oxygen attacks the alkene. All of these steps, these arrows, happen at the same time and lead to the formation of the intermediate shown. In this intermediate, the carbon-oxygen bonds are formed, and they were formed with syn stereochemistry. Because they form at the same time in a concerted fashion, they must be formed on the same face of the alkene. Then in the second step, the persulfate and water remove the osmium to form the final alcohol or diol product. The second reaction here is the oxidation of an alkene with O3 or ozone. And in this reaction, the ozone cleaves the carbon-carbon double bond to form two carbonyl compounds. The carbon-carbon double bond is cleaved. And to each end of that bond, each carbon forms a new carbon-oxygen double bond, resulting in 2 new carbonyl compounds. Here, those carbonyls or ketones are the same because we started with a symmetrical alkene. But if we started with an unsymmetrical alkene, where the 2 sides of the alkene are different, then we would form 2 different carbonyl compounds as the products. The last reaction we'll see is the addition of a carbene to an alkene. And this reaction is a lot like the formation of the epoxide, the 3-membered ring with an oxygen in it, but now forms a 3-membered ring of only carbons, a cyclopropane ring. This diiodide reagent and the metal species, the zinc-copper alloy, will combine to form a carbene. And a carbene is a carbon that has 2 groups on it. Here they're hydrogens. It has a lone pair and an empty p orbital. And this means that carbenes are both electrophilic at the empty orbital and nucleophilic at the lone pair. So when carbenes react with an alkene, the alkene will attack the empty orbital, the electrophilic site, and then the nucleophilic site, the lone pair, will attack the other carbon of the alkene. And this results in 2 new carbon-carbon bonds and a 3-membered cyclopropane ring. These steps happen at the same time, and both of the new carbon-carbon bonds must form on the same face of the alkene. The concerted nature of the addition leads to syn stereochemistry. We'll end this lecture video with the question we saw at the beginning, to predict the products of 3 different electrophilic addition reactions. In the first reaction, the hydrogenation, we should remember that this is a concerted reaction that adds 2 hydrogens to the same face of the alkene. They can add to the top or bottom face of the alkene, so we'll draw both products. Then, looking at the 2 products we drew, we see that they're identical. So we form only one product in this case, the alkane with syn addition of the hydrogens. In the second reaction, the hydroboration oxidation reaction, the borane adds to the alkene in a concerted fashion, and the boron is then replaced with an alcohol. Okay, so overall, we add a hydrogen and an OH to the alkene, and they add with syn stereochemistry. They can add to the top or bottom face, and because we've added 2 different groups here, those 2 products are not the same. They're enantiomers, and both will form in this reaction. Finally, in the third reaction, the addition of a halogen or chlorine will occur through a chloronium ion intermediate that is then opened. This pathway adds 2 chlorines to the alkene with anti-selectivity. The halonium ion can be opened at either position, either carbon, and this leads to 2 enantiomers of the product.